All right, calculus nerds. So we're transitioning into differentials, which is going to be assignment number 19. And you see here we have a curve, a value of x, and the corresponding f of x on that curve. And then, of course, we have the tangent line that passes through that specific point on the curve. You might want to pause the video right now and draw that on your own paper if you wish. I will probably continue here. So again, just remember, you can pause at any time if you need to catch up with the picture. And I will do my best to give you that opportunity. I'll step out of the way each time I add something new to it, and if you need to pause. So we have again our point on the curve, on the function, and then I drew the tangent line in a different color to make it stand out. So what we're about to talk about here is, and this would be the notes page that was uploaded, so you don't need to worry about writing it down. I'm just wanting to talk through the symbols as they apply to this picture, all right? So this is just an introduction. So we're going to talk about the different labels we use for the tangent line as opposed to the function, and we'll get into talking about what we call the change in y on each of them, and then later on the change in x. All right, so let's build the picture up a little bit here, and just want to make sure I get this in the proper order. So let's say we take that x and we move forward on the x-axis. We could go backwards, but just for the sake of argument, we move forward here a certain amount. All right, and you might remember we would call that the change in x, and that would be symbolically delta x. And so this new point, this new number on the x-axis would be what? X plus delta x, wouldn't it? All right, and then if we go up to the curve and plot that point, wouldn't this over here be called f of x plus delta x? You all agree, right? Exactly, okay. Thank you, I appreciate that. So we've got that. Let's see, what else are we going to put here now? I guess that would be enough to get the conversation started a little bit. Well, first of all, let's go over here to the tangent line. Well, on that tangent line, let's see. So if we were to come to this point on the tangent line, let's label some things here. Lines, it's pretty easy to talk about slope here. So with that slope of that line, if you traveled from this point to this point, we call this the change in y, otherwise known as dy, and we call this the change in x. You might remember when we talked about tangent lines, the slope of a tangent line is called symbolically dy over dx, isn't it? So the slope of that, so the change in y on that tangent line would be, if we took the derivative, which is called dy dx, also known as f prime of x, all right? And if we only wanted to know what the change in y was, the change in y, otherwise known as dy, all we'd have to do is treat this like an algebra equation and multiply both sides by dx. I hope this is the order it comes up. And dy, therefore, if you multiply both sides by dx, would equal f prime of x dx. That's called a differential, the change in y. The derivative is a rate of change between two variables, whereas dy is just the change simply in y. So we'll talk on some future examples about finding a differential for a particular variable. So there's a big difference between a derivative, which is a rate of change, and simply a differential, which is just the amount of change. So rate of change as opposed to amount of change. So hopefully that made sense. Like I said, we're all doing our best here. Now, let's jump over the other column. What do we call the change in y as it occurs on the function? So here's dy, the change on the tangent line. As far as the function, the change in y that would occur from here to here, we call that delta y. All right, so there's a difference there. And so delta y is the change on the function. All right, we're going to talk a little bit later about how delta y and dy aren't going to be the same, are they? In fact, let's go ahead and put that there. There's going to be a gap between the change on the curve and the change on the tangent line, this gap in here. All right, so they're not always going to be, the dy and the delta y aren't always going to be the same. In fact, they're approximate to each other. So you see, that's why we put that approximate symbol in your notes there. The dy, the change on the tangent line, and the delta y, the change on the curve, the function, are different. There will always be a little gap there between them. I don't know if you can see that, but I put that in green there, that green little gap. All right, so they're approximate. Now, another thing to keep in mind would be the smaller your delta x, the less that discrepancy, right? So the dy and the delta y would be closer and closer to each other the smaller the delta x, right? And we're going to talk later about how, if we're going to use this tangent line to approximate this curve, we want to use relatively, quote, small values of delta x. The closer that secondary point, the smaller the discrepancy between dy and delta y. But I spread them out on the picture just so you can see that difference there. All right, as far as the change in x on the two, between the tangent line and the curve, well, if you look at it, dx would be the change on the tangent line, and delta x would be the change on the curve. If you look at it, those would always be exactly the same. So that's another thing to keep in mind. Dx and delta x would always be the same. So you have those notes, and we'll come back and revisit this picture when we do some questions involving differentials. But I'll point out again that this is called a derivative, this is called a differential. So there's just a very minor distinction between the two. The other thing that this picture can help us explain, and I will ask you, again, this picture is going to be relevant for both Roman numeral 1 as well as Roman numeral 2. I'm going to have to erase it to make room for future examples. So I'll just tell you, pull up that picture again, if you will. Sorry, I would leave it on the board, but I'm going to run out of room here. But when we talk about linear approximation, here's the deal. And let's build this out. The thing at the bottom is really going to be the relevant thing. When we're going to use a tangent line as a linear approximation to a curve, here's the relationships. So if we wanted to figure out this f of x plus delta x over here, all right, if that was our goal, to figure out f of x plus delta x, here's the deal. Wouldn't that be equal to f of x plus delta y? Because that's the change on the function, isn't it? So if you started here at f of x and added the delta y, that would get you exactly up there to that point on the curve, wouldn't it? So that's why it says exactly. But this is where approximation takes place. Notice the next symbol in the notes, we change the equal sign to an approximate. And why is that? When we make the leap from this step to that, notice what happened. We replaced delta y with dy. So what did we do there? We replaced the change on the curve, which gave us the exact value, to the change on the tangent line. We're replacing delta y with dy, and that's going to be off a little bit, isn't it? Okay, so that's why it says approximation. So what happened in that step is we're making the leap from curve to tangent line. And when we do so, we've lost some exactness. It's now approximate. All right? Then, I want to remind you that we mentioned, so let's take a look at dy. Didn't we mention earlier that dy is equal to f prime of x dx, right? So, if we replace that dy in that previous discussion with just that, remember dy is equal to f prime of x dx, so this is just replacing this with something it's equal to. All right, and then, remember we also said on that earlier slide that dx is equal to delta x. dx is equal to delta x. So if we replace the delta x for the dx in this thing, we get that. And there you go. So if you start with this, and this is essentially a proof of the thing that's at the bottom of that slide. We're going to be asked to do some what's called linear approximation later on. And basically we're going to take this f of x plus delta x and do this to it. So this literally is the bottom line for that discussion keep this in mind. I'll pull this slide up when we're later on going to be asked on some future examples to do linear approximation. All right, so that's the background for this particular section. And now we'll jump in and we'll start out doing some differentials and some linear approximation. And it sounds like a party, doesn't it? All right, we'll see you in a few. Keep that picture handy.